At a maintenance facility in San Antonio, a $400 million Boeing 747-8 sits in a hangar. It was built to carry a royal family in conditions that make a five-star hotel look functional. Right now, if someone fired a shoulder-launched missile at it during takeoff, there is nothing aboard that would stop it. That aircraft has been proposed as the next Air Force One. The question is not whether it is luxurious enough. The question is whether it can be turned into a flying fortress before the clock runs out. Before we dive in, comment where you are watching from and click subscribe. Air Force One is not an aircraft. It is a designation, a radio call sign assigned to any United States Air Force fixed-wing aircraft carrying the president. In operational reality, it refers to one of two Boeing VC-25A aircraft that have transported every president since George H.W. Bush. Those aircraft entered service in 1990. They are 35 years old. Parts are increasingly difficult to source. Maintenance windows have grown. The purpose-built replacements, two new 747-8s designated VC-25B, have been under contract since 2018, are billions over budget, and are not expected to deliver until 2027 at the earliest. Into that gap, the Qatari royal family has placed a gift, a 747-8 Intercontinental, delivered new in 2012, and configured to a standard of interior luxury that has no equivalent in any government aircraft currently flying. The aircraft is real. The offer is accepted. The engineering problem that follows is one of the most demanding retrofit challenges in the history of military aviation, and the outcome is genuinely uncertain. Start with what the aircraft actually is. The Boeing 747-8 Intercontinental is the largest, fastest, and most fuel-efficient variant of the most recognizable commercial airframe ever built. It measures exactly 250 feet, 2 inches from nose to tail. That is 20 feet longer than the current Air Force One and only 14 feet shorter than its own wingspan. Stand it on its tail and the nose would sit level with the roof of a 19-story building. The fuselage reaches 19 feet across at its widest point, producing a main deck cabin width of 20 feet, an interior dimension that allows genuine room-sized spaces rather than the corridor with seats geometry of most aircraft cabins. The wingspan spans 224 feet, 5 inches. Winglets curve upward another 11 feet at each tip. Those winglets are not aesthetic flourishes. They interrupt the vortices that form at wingtips during lift generation, to recovering energy that would otherwise dissipate as turbulence and converting it into roughly 2% additional fuel efficiency. On an aircraft burning approximately 2,800 gallons per hour at cruise, 2% is not trivial. The wing area totals 5,963 square feet. 4 General Electric Jenks, 2 B67 turbofan engines power the airframe. Each produces 66,500 pounds of thrust, 14,000 pounds more per engine than the CF680C2 units on the current Air Force One. They achieve this while burning 15% less fuel per pound of thrust, a gain made possible by a bypass ratio of 8:1. For every pound of air that passes through the combustion core, 8 pounds flow through the fan section and around the core entirely. That outer flow of cold air generates the majority of the thrust. The core provides the energy to spin the fan. Higher bypass means greater efficiency, lower acoustic signature, and a smoother ride at cruise altitude. The fan diameter measures 104.7 inches, nearly 9 feet across, with 18 carbon fiber composite blades. Those blades weigh 50% less than equivalent titanium components while handling identical structural loads. The combustion section operates at 2,400 degrees Fahrenheit at cruise. Ceramic matrix composite materials line the combustion chamber and turbine section, materials that were not available when the engines powering the current Air Force One were designed. These ceramics sustain temperatures that would deform conventional metal alloys, allowing the engine to run hotter and therefore more efficiently without shortened service life. Maximum takeoff weight reaches 987,000 pounds. An empty weight sits at approximately 485,000 pounds, leaving more than 500,000 pounds available for fuel, passengers, cargo, and systems. Fuel capacity reaches 63,000 gallons distributed across wing and center fuselage tanks. At cruise consumption rates, that translates to more than 22 hours of flight time before the aircraft requires additional fuel. Range without refueling is 8,000 nautical miles, enough to reach Washington to Singapore, Washington to Dubai, or Washington to virtually any capital city on Earth nonstop. The current VC-25A is limited to 6,800 nautical miles and burns 16% more fuel to cover that shorter distance. Cruise speed sits at Mach 0.855, approximately 570 miles per hour at altitude. Maximum operating speed reaches Mach 0.9 before aerodynamic limits impose a ceiling. Service altitude tops out at 43,100 feet. The airframe is 13 years old. That number sounds problematic until it is placed in context. The aircraft the Qatar jet would replace has been flying presidents for 35 years. The 7478 airframe is certified for 35,000 flight cycles and 135,000 flight hours. A VIP transport configuration accumulates a few hundred cycles per year under careful handling and climate-controlled hangar storage. This aircraft is, by any reasonable engineering assessment, early in its service life. What the Qatari royal family built inside that airframe is the conversion challenge in concentrated form. Step through the main entrance door and the architecture immediately signals its original purpose. A private hallway leads directly to the presidential suite. No commercial boarding process, no contact with other passengers or staff. The forward section of the main deck, space that a commercial 747 fills with business or first-class seating, is occupied entirely by a master bedroom suite. The bed is not a fold-out. It is not a convertible sofa. It is a king-size bed with a full mattress, structurally mounted to the airframe in a configuration engineered to remain stable through turbulence. The current Air Force One has a pull-out bed that presidents have complained about for 3 decades. The surrounding woodwork is custom millwork with hand-selected grain patterns matched across adjacent panels. This is a category of craftsmanship associated with super yacht interiors, costing thousands of dollars per linear foot and requiring specialists who work only in aviation and maritime luxury applications. Indirect LED lighting is integrated into ceiling coffers. Climate zones allow independent temperature control isolated from the rest of the aircraft. The master bathroom connects directly to the bedroom suite through a dedicated door and contains marble countertops, gold-plated hardware, and a multi-head shower with water pressure that belongs in a residential bathroom rather than a pressurized aluminum tube. A second master bedroom occupies additional space further aft, or because the original configuration assumed more than one principal requiring that level of accommodation. Moving forward from the bedroom suite, the private office occupies the next section. The desk is sized for actual executive function, not a folding surface. The chair is leather-mounted on a swivel base that locks during turbulence. Built-in display screens, storage, and work surfaces are integrated into the wood-paneled walls. The current VC-25A's office is functional and reflects what modern meant in the mid-1980s. The Qatar jet's office looks like a Manhattan corner suite condensed to fit a cylinder moving at 570 miles per hour. The main lounge is the centerpiece of the interior. Leather sofas arranged for conversation. Individual armchairs that swivel and recline. An entertainment center integrated into a wood-paneled wall with screens and speaker systems designed for a home theater environment. Ceiling height reaches nearly 8 feet, a dimension that requires active engineering effort to achieve in an aircraft fuselage, and that produces a cabin atmosphere qualitatively different from any comparable airborne space. The windows are larger than standard commercial specifications, and electronically controlled shades dim from transparent to opaque at a touch. Upstairs, the 7478's upper deck runs 60 feet from the cockpit door to the rear pressure bulkhead, providing approximately 1,000 square feet of additional cabin space. A curved staircase with polished wood handrails and leather-trimmed treads connects the 2 levels. On the Qatar configuration, the upper deck holds additional lounges, seating areas, and a full galley. The crew quarters and pilot rest areas occupy the forward upper section. For the Qatari royal family, the staircase was an elegant architectural feature. For the Secret Service, it is a choke point that must be monitored, controlled, and defensible from multiple positions simultaneously. None of this is what makes the retrofit difficult. What makes it genuinely challenging is the gap between what this aircraft contains and what Air Force One is required to contain. The current VC-25A carries what program documentation describes as the most sophisticated airborne communications suite in the world. Encrypted satellite uplinks, secure video conferencing systems, direct lines to nuclear command authority, the capability to broadcast to the nation from 40,000 feet. That equipment fills entire sections of the aircraft, server racks, cable routing through every bulkhead, dedicated cooling systems to prevent electronic hardware from overheating at altitude. The upper deck of the VC-25A is not a lounge. It is a flying data center with seating attached. The Qatar jet's upper deck has leather sofas and wood paneling. The equipment that needs to occupy that space does not exist on this aircraft yet, and finding room for it without visibly compromising the interior that justified accepting the gift in the first place is the central engineering constraint. Add the defensive systems requirement and the problem compounds. The Qatar jet's current threat protection consists of a ground intrusion alarm. That is the complete inventory. For a royal family operating within its own security perimeter on its own territory, that was an adequate configuration. For the President of the United States, it represents a protection posture approximately equivalent to 0 against any serious aerial threat. The ALQ-204 Matador system addresses the most statistically likely threat category: shoulder-fired infrared-guided missiles. The SA-7, the Stinger, the Igla, and their variants all use cooled infrared seeker heads, typically indium antimonide detectors sensitive to specific heat wavelengths produced by jet exhaust. The seeker identifies the engine heat signature against the cold sky background and guides the missile toward that contrast. The Matador defeats this guidance mechanism by blinding the seeker. Infrared sensors mounted on the aircraft detect the ultraviolet flash from a missile's rocket motor at launch. The detection signature is distinctive and visible at range. Within less than 2 seconds of detection, the system calculates the missile's approach trajectory and directs a high-powered infrared laser onto the incoming seeker head. The laser saturates the detector with energy at the same wavelengths the seeker is using to track the aircraft. The seeker cannot distinguish the real thermal target from the jamming energy. Guidance lock breaks. The missile flies off course. The entire sequence, from launch detection to guidance disruption, occurs faster than a human operator could consciously identify the threat. Chaff and flare dispensers handle the remaining missile threat categories through different mechanisms. Chaff consists of metallic strips, typically aluminum-coated fiberglass, cut to lengths corresponding to specific radar wavelengths. Ejected into the airstream, the cloud creates a radar return larger than the aircraft itself, drawing radar-guided missiles away from the real target. Flares operate against infrared seekers through thermal deception rather than electronic jamming. Each flare burns at approximately 2,000 degrees Fahrenheit, substantially hotter than jet exhaust, presenting a more attractive heat source that pulls heat-seeking guidance systems off the aircraft. Modern infrared-guided missiles incorporate discrimination algorithms that attempt to distinguish flares from engine exhaust based on spectral characteristics and movement patterns. Modern flares incorporate spectral coatings that mimic jet exhaust emissions, defeating those discrimination systems. Electronic warfare systems address radar-guided threats by detecting incoming radar signals, characterizing their waveforms, and broadcasting interference that prevents the radar from developing a weapons-quality targeting solution. The specific systems are classified. The principle is standard. Deny the hostile sensor the coherent return it requires to guide a weapon. EMP hardening may be the least visible and most consequential requirement. An electromagnetic pulse from a nuclear detonation at altitude or from a purpose-built EMP weapon destroys unshielded electronics instantaneously. Every computer, every communication processor, every flight control system would fail simultaneously and without warning. Air Force One must remain fully operational through an EMP event of the highest anticipated intensity. That requirement means every electronic system aboard requires Faraday shielding, a continuous conductive enclosure that distributes electromagnetic energy across its outer surface rather than allowing it to penetrate to the electronics within. The critical word is continuous. One gap in the shielding, one unsealed cable penetration, one improperly bonded panel, and the protection fails entirely. On aircraft designed for military use, Faraday shielding is integrated into the structure during initial construction. On the Qatar jet, it must be installed retroactively behind wood paneling and leather surfaces that were engineered to conceal luxury, not electromagnetic protection. This is the constraint that makes analysts skeptical and that prompted aviation analyst Richard Abulafia to describe a quick conversion as a fantasy. The technical capability to install all required systems exists. American aerospace contractors have been hardening aircraft and integrating military electronics for decades. L3 Harris Technologies, which will handle the retrofit in San Antonio, has relevant experience across multiple military modification programs. The constraint is not capability, it is geometry and sequence. Every modification must fit behind surfaces that were not designed to accommodate it. The wood paneling must hide Faraday shielding, the ceiling must conceal antenna feeds, the floors must route cable bundles to systems that have no designated spaces. The communications suite alone requires hundreds of square feet of equipment, satellite terminals, encryption hardware, video conferencing infrastructure, and the redundant backup systems that ensure connectivity even when primary systems fail under hostile conditions. On the purpose-built VC-25B, each piece of that equipment has a designed compartment with engineered cooling, dedicated power, and planned cable routing. On the Qatar jet, engineers must find equivalent space in an airframe optimized for a fundamentally different purpose, without producing a final product that looks like military hardware bolted into a palace, because the visible preservation of the interior is part of what justified the conversion in the first place. Cost estimates reflect that uncertainty. The aircraft arrived without a purchase price. Retrofit projections range from $100 million at the low end, and covering basic defensive systems and communications capability, to over $1 billion at the high end for full VC-25B equivalency, with every system, every redundancy, and every classified capability the purpose-built aircraft will deliver. The range itself illustrates how much remains undetermined about scope and timeline. Expert estimates for completion span 18 months to several years. If the conversion completes quickly and successfully, the Qatar jet bridges the operational gap while the VC-25B program finishes its delayed delivery schedule. If it takes longer than the VC-25B program, the current 35-year-old aircraft keeps flying presidents until the purpose-built replacements arrive, and the Qatar jet transitions to the Presidential Library. It is contractually required to enter by January 2029, if not in government service by that date. That deadline is the defining pressure on the entire program. The engineers in San Antonio are not working against an open-ended timeline. They are working against a fixed contractual endpoint that moves backward from January 2029. Every month of delay compresses the operational window the aircraft could actually serve. Every engineering decision that adds complexity adds time. Every system that requires custom integration rather than standard installation adds both. What sits in that San Antonio hangar is genuinely extraordinary as an aircraft. Its range exceeds current Air Force One by over 1,000 nautical miles. Its engines produce more thrust while burning less fuel. Its interior represents a standard of airborne luxury that no head of state aircraft currently in service approaches. It was free. The problem is that none of those qualities are what make Air Force One what it is. What makes Air Force One what it is has nothing to do with comfort and everything to do with survivability, communications, and the ability to function as a mobile national command authority in conditions where everything on the ground has already failed. That capability does not exist on this aircraft yet. Installing it means hiding a fortress inside a palace without destroying the palace that made the fortress worth building in the first place. Whether the engineers in San Antonio can do that on the timeline the contract requires at a cost the program can sustain, it is the question that the aircraft itself cannot answer. The airframe is ready. The clock is running.